Hey everyone, let's jump right into this. Did you know that enough sunlight hits the Earth in a single hour, just 1 hour, to power the entire globe for a full year? It's literally mind-blowing. Today, we're going to demystify the microscopic science behind something we see every single day, but, rarely actually understand. We're going to figure out how we capture that incredible power, taking a really fascinating journey from a single beam of sunlight all the way to flowing electricity.
Okay, let's dive into this. Have you ever looked up at a massive solar array on a roof and wondered, how exactly does a simple, completely invisible photon from the sun actually transform into the electrical power that runs our homes? Well, to understand this, we have to scale down. Like way down, because that giant solar panel on your roof, it isn't just one big solid sheet. It's actually a collection of many tiny individual units called solar cells. And the real magic, the whole shebang, happens inside each of these tiny little cells.
To truly grasp this, let's just pretend we're structural architects for a minute, okay? The absolute foundation of our solar cell is a metal conductive plate. You can think of this as the floor, our positive electrode. Next, we bring in the real star of the show, the semiconductor layers. We lay down a bottom layer made of silicon mixed with boron, and right above that, a top layer of silicon mixed with phosphorus. Over both of these goes an anti-reflective coating, which is specifically designed to trap as much incoming light as possible. And finally, capping it all off like a roof, we install a negative electrode. So boom, that's our complete physical architecture.
Now, what's really interesting about this slide is the duality of those two middle semiconductor layers we just built. We don't just use one plain, boring block of silicon. Actually, we essentially have two totally distinct chemical personalities stacked right on top of each other. The top layer, the one mixed with phosphorus, is what we call the N-type semiconductor layer. And the bottom one, mixed with boron, well, that's the P-type semiconductor layer. This careful pairing of contrasting materials isn't an accident. It's absolutely intentional, and it forms the literal core engine of our solar cell.
So, because we have these two highly contrasting materials pressed right up against each other, a really critical boundary forms exactly where they touch. We call this microscopic meeting point the p-n junction region. It sits directly between the top silicon phosphorus layer and the bottom silicon boron layer. You can basically think of this p-n junction as a highly sensitive, electrically charged border zone. It connects the two layers and just sits there, perfectly still, waiting for a catalyst to kick things off.
But wait, before we introduce that catalyst, let's glance back at the very top of our cell again, where that negative electrode sits. If you've ever walked past a solar panel and noticed that shiny silver grid on top, well, we can demystify that engineering jargon for you right now. Those very thin stripes running across the cell are called fingers, while the thicker, much more prominent stripes that connect them together are known as bus bars. And they are just there to look cool. They are the literal structural highways that are eventually going to carry our electricity away.
Okay, the stage is perfectly set. The physical architecture is completely built. Now the action actually begins. Imagine the sun rising. A beam of pure sunlight hurtles through space, strikes our anti-reflective coating, and bam! We immediately transition from static architecture to high-speed microscopic physics.
And this brilliantly illustrates the invisible rapid chain reaction caused by the sun. When that light hits, the reaction is literally instantaneous. Sunlight is made of tiny little packets of energy called photons. When these photons crash into the cell, they transfer their energy directly into the electrons that are trapped inside our silicon layers. With this sudden massive burst of energy, an electron jumps up to a higher energy level and completely breaks free from its atomic bonds. But here's the really fascinating part. When an electron leaves its spot, it leaves behind an empty space, which scientists literally just call a hole. Because of that p-n junction border zone we mapped out earlier, the newly freed excess electrons are forced to move up into the n-type layer, while those empty holes, they're pushed right down into the p-type layer.
So the crucial point here is that this isn't just happening to one solitary electron. No way. This reaction is happening millions of times a second across the entire surface of the cell. We suddenly have vast numbers of excess electrons rapidly collecting at the very top in the n-type layer, while all the corresponding holes are gathering down at the bottom. This creates a massive buildup of electrical potential. It is exactly like water building up behind a dam, just bursting with restless energy, desperately waiting for a path to escape.
Let's see how this builds and how we actually unleash that dam. All those hyperactive excess electrons up at the top desperately want to reunite with the holes down at the bottom. But the catch is they can't go backward through the p-n junction. So when an external supply is connected, like say a wire running from those top fingers and bus bars all the way down to the bottom metal plate, those excess electrons finally have an escape route.
the powerful attraction pulls them right through the wire toward the holes. And that steady, massive flow of moving electrons through the wire, that is exactly what flowing electricity is.
It's truly a marvel of modern engineering, isn't it? Just imagine the millions of invisible electrons jumping around on your roof right now, completing this microscopic journey second by second, silently powering your lights, your screens, your whole life. The big takeaway for us today is that the biggest energy revolution on Earth is actually happening on a microscopic scale. As this tiny science becomes more and more efficient, how will it completely reshape our massive modern world tomorrow? Something to think about, right? Thanks for exploring this fascinating invisible world with me today.